Okay, hello everyone. My name is Matthew. This is my YouTube channel. You can see I have a green screen right here. And for this video, we're not going to do anything because I need to work out the kinks with that. But yeah, that's cool. Anyways, we're here for chemistry, as you can see by the title of this video. Chemistry. Okay, so basically this is for my my classmates, right? For my chemistry class. Everything I have here for my setup is all from my personal savings account, my checking account. All the money. It almost fell. All of this, the lights, the green screen, the stand for the green screen, all me. So I value the people I try to help, and it's sticking to me. Okay, ignore that. So basically, this is a study guide review. If I was more experienced and I knew how to use the green screen, I would use that and put like stuff right there. Like a periodic table, hydrogen, helium, lithium, beryllium, boron, so on, you know, all that. But basically, so this is very simple. Once you understand it. So we're gonna start with electron configuration. It's a little goofy. Can you stop sticking to me, please? Oh shoot, it was actually falling. Did not know that. Electron configuration. It's a little. It's simple. It's not too difficult. I think you'll get it, viewer. It's not that bad. Anyways, so basically, for electron configuration, you have the. I wish I know how to edit it. I don't. I'm not an expert with this. You have the S block right here with the starting with hydrogen. It includes helium too. So like technically for this purpose, helium would have to be over here, but it's not. It's whatever. Don't mind it too much. It's only over there because it's a noble gas. Okay. So the S block is right here. Hydrogen all the way down to francium. Helium included all the way down to radium. Radium. Radon's over there. So basically, that's the S block. The orbitals. There is one orbital in the S block. The orbitals are what determine, like, I actually don't know. Okay, actually, let me look. An orbital is a function that describes the location and wave-like behavior of an electron in an atom. If you didn't get that, I didn't either. So that's just from Google. I looked that up. Okay, an orbital is basically where an electron can be, and each orbital can hold up to two. Count them. 1, 2 electrons. Okay, very simple stuff. And the S block has one orbital, as you can see. 1, 2, or 1, 2. It has two atoms, or two elements in it because it has one orbital. One orbital holds two. Very simple. Orbital 1, or no, orbital 2, 2s, so 2, the second orbital of the s block has lithium and beryllium in it. Easy stuff. Super simple. The 7th orbital in the s block has francium and radium in it. And you guys can't really read that. Yeah, at a time like this would be very helpful. It's whatever. I'll do it for the next video. But yeah, that's the orbitals. Now, there are 4 different blocks: the s block, the p block, the d block, and the f block. Super simple stuff. It's just the location of it. Or no, it's in a different orbit. Okay, start over. The p block has 3 orbitals. The d block has 5 orbitals, and the f block has 7 orbitals. Okay, so the s block consists of the alkali metals and the alkaline earth metals. Easy stuff. Easy stuff, especially for you smart people. Like, you're taking chemistry, you gotta be smart for that. Super easy stuff. Okay, now we move on to the p block. It's boron, carbon, nitrogen, oxygen, fluorine, neon, and all the way down from there. Okay, so ignore these right here is zinc, cadmium, mercury. Those, ignore these. Ignore this. Okay, it's just what you see here and not helium. Okay, super simple stuff. These these 30 elements right here that you see, and not those down there. These 30 elements are the p block. It is 3 orbitals, because 1, 2, that's 1 orbital. 3, 4, that's a 2nd orbital. 5, 6, that's the 3rd orbital. Easy. And that's how it goes all the way down. 1, 2, 1, 2, 1, 2, 1, 2, 3, 4, 3, 4, 3, 4, 3, 4, 5, 6, 5, 6, 5, 6, 5, 6. Easy stuff. That's the orbitals. Yeah, very easy. And the D block is this right here, from scandium, all the way to zinc, and all the way down, not including these, not including the lanthanides and actinides. Ignore those. That's the F block. We'll get to that in a minute. But these, all right here, those have 5 orbitals per row. Okay, 5 orbitals, because it's 1, 2, that's 1 orbital. 3, 4, that's 2 orbitals. 5, 6, that's 3. 7, 8, that's 4. 9, 10, that's 5 orbitals. Easy, super easy. And then the F block down there, the lanthanides and actinides. Lanthanides, actinides. Is that how you say it? Actinides? I don't know. The point is, it's 7 orbitals because it's 14 elements. 14 divided by 2, 7. 2 because it's 2 electrons per orbital. Easy stuff. Okay? So, it's 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Easy. Okay, if you have lanthanum down here and actinium down there too, and lutetium, and lawrencium are still down there, your periodic table is bad. It's not a good table, okay? It's got to be 14 down there. So if lanthanum and actinium are down there, then lutetium and lawrencium have to be up here, okay? If not, bad periodic table. Do not use that, okay? Don't use it. It's a bad periodic table. And for that matter, lutetium, and lawrencium are supposed to be down there anyways. So if lanthanum and actinium are down here, bad periodic table. regardless of what's up here. If it's not actinium and if it's not lanthanum, bad. Okay? I'm getting tired speaking. I think you can probably hear it, like panting, like. Okay, so please stay with me here. And those are the 4 different types of orbitals. Okay, easy stuff. The way the orbitals work is kind of goofy, because see these numbers on the side? The numbers of the columns 1, 2, 3. Okay, it's backwards. It's flipped. I don't know why. 1, 2, 3, 4, 5, 6, 7. There's 7. 7. Okay, 1 through 7. That is the row. Ignore that. That's the row, right? That it's in. Easy. Here's where it gets a bit confusing. The orbitals are organized. So it's 1s is hydrogen, helium, because there's the 2 in the 1, and they're in the s block. Okay? They're in the s block, and they're in the first row. So they're together. 2s, lithium and beryllium, they're in the s block, and they're in the 2 row. The 2s, okay? That's that. That's how it goes all the way from for the s's and the p's. That's how simple it is. Hang on. My phone is like falling. The phone stand is not very good. It's whatever. That's how it is for the p's and the s's. The p's over here, these 30s, these 30 elements, that's how it is for them too, right? The p block, okay? So that's how it is for them too. There's 3p, 4p, 5p, 6p. It's technically 7p, but that's way too complex. Plus oganesson, I think is the name. Oganesson is has a half-life too short for us to measure it, for it to be useful, for it to exist. Basically, it's a matter of milliseconds. It exists and then doesn't, and it keeps falling. I don't know why. Hang on. It keeps tilting. That's it. Okay, so we're good for now. The 118 oganesson, it's not on this periodic table because it's too short of a half-life, and that doesn't. We're just gonna have it like that, so it tilts over like the other way slowly. Okay, so that's how that works. Actually, that's annoying me. Whatever, we'll keep it like that. Don't care if it tilts over like that. So the last 1, 2, 3, 4, last 9 elements on this periodic table is missing because they have such short half-lives. It doesn't even like matter if they exist because they're not useful for measuring electron configuration, for using that. Okay, right? So with the D block and the F block, it's a bit different. Okay? So the D block, it doesn't have, I can't give you really an explanation for it, but it's, when it says 4 right here, it's actually going to be a 3 for the Ds. Okay? It's not going to be a 4. It's not going to be 4D. 4D is actually in the 5 row. This is the 4D. This is 3D, 4D, 5D, 6D. 7D, if it existed, would be below that. And it doesn't exist because there's no 8S or 8P. Okay? It's one behind. So what the number is right here, you subtract 1, and that's the number for the Ds. Okay? And then, so if it's 4D, it's actually going to be in the same row as the 5P and the 5S. Okay, so if it's 5S, 4D, 5P. Okay? That's that. That's how the Ds work. Okay, don't know why I do know why. Don't know how to explain it. Don't remember why. We shut up. That's why. I know the reason why. I just don't know it by memory. It's got to do with like the way it orbits the nucleus. Right? I don't have the notebook with me right now. It's downstairs. I don't care to go get it right now. But it's whatever. I'll show you in the next video. But it's like goofy. I'll try to actually. I might actually try to put it up here. The picture of the way they orbit. It's terrible. Don't try to remember it unless it's required for your class. Don't mess with it because it's gonna overcomplicate it. There's one orbit. This is off topic. It's either for D's or the F's. I don't remember. But there's an orbit up here, a donut orbit in between, and an orbit right here, and the nucleus is in the center. Okay, whatever. There's also the P orbit, because S orbit is just like the regular circular orbit, right? That you see everywhere. So lucky I bought these. I have dumbbells in my room. The P orbit is like that. There's one for the first orbital. The second orbital is like that. And the third orbital, hang on. Is like that. So it's like one going like that, one going like that, and one going like that, right? Like a three-dimensional cross. Doesn't make sense. Yeah, it doesn't make sense. But don't mess with that unless it's required for your class. So that's that. The F block is even goofier because it starts right there in between lanthanum and hafnium, in between actinium and the rutherfordium. The F block is one behind the D block. So it'd be two behind the S block and the P block. The P block and the S block are on the same. So if it's two up here, it's gonna be two over there and two right here. Okay. The F block has only two different numbers. It's either 4F or 5F. It's never anything else because those elements don't exist. It's never gonna be 6S or 6F. So that's the F block. If it's only ever 4 or 5. It's only ever 4F or 5F. It's never any other number. Okay? So that's the basic rundown of it. You probably already know that going into this video. I have my chair here. So yeah, that's why I keep popping up papers from nowhere. So that's the basic rundown. You probably already know that, as I said. So the way orbital notation works is you, this is a good example. Okay, so for orbital notation, no, not orbital notation, forget that for now. We don't have time for that. For electron configuration, there is something, I don't know why. I was not paying attention in class, so my bad. But there's, with electron configuration, there's something called noble gas cores, where you go to noble gas, these last column right here, noble gases, not forget this, okay? Just right here, this last column, okay? Those are the noble gases, okay? Basically with the noble gases, you can use them as your core. I don't know how to explain that very good, but that's the best way to explain it. They're your core. The name for it is a noble gas core. So you start off at that, and you go from there to the given element. So if you're given silicon, my bad, as it is on the paper down there. If you're given silicon, where's silicon? Right there. You'd go noble gas, but 18 is too big. 18 is bigger than 14. So what you do is you go 18 up 1, because 10 is smaller than 14. You can actually map that out. So you go 14, or you go 10, then you go 3s, right? These two. So you go through 2 of them. So then what you're going to do is you're going to write it down as 3s to the power of 2, because it's 1, 2 electrons that you're going through. You're going through the first atom, or the first electron, the first element, and then you're going through the second one in that orbital. The 3s orbital, you're going through both of them. So you're going to put the 2 for both of those, the highest energy electrons in those orbitals, okay? Because you're going through both of them. You're counting through both of them, you're counting them. And then you're going to go across to P, because it's the same column. You're going across, because there's no transition metals right there. No transition metals. So you go to P, and then it's 1, and there's silicon too. So usually, if you're going to use the P's, it's going to be 6, because it's 6 elements in that row. But because silicon is the second element in that row of the P's, the second element in the P's, on the 3 P's, it's going to be 3P and then 2, because it's the second element. And then you're there. You're done. That's how you configure that. It's very simple. Random element. Carbon. Just because I looked at my chair and it's like wood's made out of carbon. I don't know. It's okay. So what you do is you go helium as your noble gas core, and the way you do this is you put it in like brackets. Right there. Right there. See, neons in brackets. It's backwards, but whatever. Neons in brackets, because that's the noble gas core for silicon. I forgot to tell you that. But it's a noble gas core for silicon, so you put in brackets, and you start off there. So as I wrote down, 3s, 2, 3p, 2. That's silicon. Back to carbon. You put your brackets. Oh, my paper is ripping. Okay, that's that. You put the brackets, and in the brackets you put He for helium. And then what you're going to do is you're going to go over to the next row. To the next row. Because you're going for carbon, right? So helium, you go over, down 1 row, down 1 row, there's lithium. So it's the 2s. So you go 1, 2. That's 2s to the power of 2. It's not actually squaring it. It's not actually putting it to the power of 2. S is not a variable. It's just a letter to signify where you are. The 2 does nothing. You cannot solve for S. Okay, there's no solving for it. Okay, you're not solving for math. It's not math. Remember that. So you got lithium, beryllium, over. You got boron, and there's carbon. So 3p2 or 2p2. Right? So the electron configuration for carbon would be brackets, helium, and close brackets, 2s to the power of 2, 2p to the power of 2. There you are. There you are. That's it. That's electron configuration. Super simple. You shouldn't struggle with it. I took 25 minutes to explain it. 24 and a half. But yeah. Consider subscribing if you haven't already. I don't care. Don't subscribe if you don't want to. Just if you need help, I'm here for you. So, thank you all for watching, and I hope you do well.